Hello, this time we'll talk about inference on two population parameters. That's chapter 12, part 2. What we're going to do is to perform a test for independence. So far, we have seen how to use chi-square test to check if the observed distribution of a variable is different from the expected distribution. This time, we'll check whether the relationship between two variables are different from their expected relationship or expected distribution. For example, we have two variables here, marital status and happiness. Marital status can take four different values, and happiness variable can take three different values. What we did is we asked about 3,000 people whether they're happy or not too happy, and if they're married or not married, or just the marital status in general. And we recorded the answers. These numbers show number of people who responded in each category. And if these variables are independent, then it allows us to check whether happiness and marital status are related or not. So our null hypothesis under chi-square independence test is that the variables are independent, and the alternative hypothesis is that null hypothesis is not true. That means the variables are not independent. The intuition is the null hypothesis is that the variables are not associated or independent. That means there is some relationship between marital status and happiness. What type of relationship? We don't know, but this is the beginning of the full analysis. So, as we know from our probability lessons that if two events are independent, let's say event E and event F, then the probability of E and F happening jointly is equal to the probability of E times the probability of F. This only happens when the probability of E and probability of F, they are not related to each other. If they are related to each other, then the probability of E will change if the uh, probability of F changes. That is, if event E is affected by the event F, then they are not independent, they are dependent. And the change in event F will also affect event E. So now we can calculate the expected distribution for these two variables. What we have here is observed. To calculate the expected distribution under the assumption that these two variables are independent, first we need to calculate the row sum and column sum. So we can use Excel file where I have already entered the data to calculate the sum across rows and the sum across columns. So let's do that. Equal sign sum the columns, then I drag this down below, and equal sign sum across rows, then I drag to far right. What does this number show? This number shows that out of all people we surveyed, total 1,413 people are married. and so on and so forth. What does this number show? That out of all people we surveyed, total 919 people responded that they are very happy. We can also sum all these numbers to get the total number. Notice that this is the sum of the sum. Similarly, if we sum these numbers, the column totals, then we are also going to get the same number. This is another sum of the sums. Okay, now we need to calculate the proportions. That means, what is the proportion of married people among total people, and what is the proportion of very happy people among total people? If these two events are independent, then the multiplication of this proportion and this proportion will result in a joint proportion or joint probability of people being very happy and married. If that probability is different from this probability, then we say our observed data differs from the expected data. So I'm going to copy this table down below and empty these cells to calculate the proportions. This over this total, and I want to drag this rectangle from here to here, but this will change this red rectangle going from G to J. So I don't want that. So I'm gonna fix that rectangle, red rectangle, right here. So I'm gonna put a dollar sign in front of G. And this blue rectangle can change as I drag this from here to here. It will go from here to here. Press enter, you get the proportion of married people among the total sample. Okay, and we have proportion of widowed, divorced, never married as well. Now if I drag it further, then I get 1. Why? Because this is basically 2985 divided by 2985. The proportion of the whole sample out of whole sample is 1, that is 100%. Similarly, if I calculate the proportion of very happy people out of 2985 people, then I get to divide 919 by 2985. But this time, as I will drag this down below, I don't want this red rectangle to move. This is right now at this position, row equals 6. I don't want it to change from 6 to 7 or 8, but I want this blue rectangle to change. So what I'm going to do, I am going to put a dollar sign in front of 6, that is for the red rectangle, and fix it right there. Then I'm going to drag this down below to calculate all this proportion for very happy, pretty happy, and not too happy. Now that we have the proportions ready for all events, we can multiply these proportions to calculate the probability of being married and very happy, being widowed and very happy, being divorced and very happy. It's just all multiplication. So this is 0.473 probability of being married times 0.308 probability of being very happy. And then I press enter. So this is the proportion. That means if these two events are independent, we expect that the proportion of married and very happy people is 0.146. That means 14.6% people, we expect them to be married and very happy if these two events, these two variables are independent. Now I have to calculate the same for all these cells. What I can do, I can put, since I'm gonna drag this rectangle down below, I need to fix the cells. So right now I'm in C10. I want to drag this right here, and I don't want this blue cell to go from here from 13 to 14. So I'm gonna put a dollar sign in front of 13. And then for the red rectangle, I don't have to do anything. If I drag this rectangle down, then it will come with me. Now I have these proportions calculated. Similarly, when I drag this rectangle to the right, it will change the blue rectangle going from here to here, but it will also change the red rectangle going from here to here. And I don't want that. So I don't want to change from G to H. So I'm gonna put a dollar sign in front of G. And then drag this here. And now I can drag the rectangles because I've already fixed the rows and columns that I don't want to move. Now that we have all the proportions ready, for example, we have never married and not too happy, this proportion ready as well. What does it mean? That the proportion of people in the sample who are never married and not too happy is 0.032. That means 3.2% of people are never married and not too happy if I expect these two variables to be independent. So this table right here gives the observed values, and this table right here gives the expected proportions, expected proportion. But if I want them to be expected numbers instead of proportions, what do I have to do? I have to multiply these proportions with the total. Remember our formula, expected value is equals n times p, and p is the probability, n is the total number. When you multiply them together, you get the expected value. For example, if p is the probability of obtaining a head, that means you flip a coin, you get if the probability of getting a head is 1/2, and you flip 10 coins, n equals 10. 10 times 1/2 is 5. That means if you flip 10 coins together, you are expect to get 5 heads if the coins are independent. So now we have these expected values, we can calculate the numbers. So this proportion times 2985, I can just type it, or I can use the formula by clicking on this. So now I get to fix this G6 because this cell is going to move as I drag this cell. So fix G and fix 6 as well. So 435. That means if the marital status and happiness, these variables are independent, we expect 435 people to be married and very happy if these are independent. But what we observe is 600 people reported they are married and very happy. Similarly, we can calculate the number of people for all these cells. First go this way, and then this way, and then okay. Now, just out of curiosity, the number of people we calculated for each cell, their sum needs to be equal to this total sample size. So why don't we check the sum? So sum of all these numbers equals to, lo and behold, it's 2985. which is equal to the observed sample size. Now, to calculate the chi-square, what do we have to do? We have to use this formula here. Observed minus expected square for each row divided by expected. Then we sum across the rows or the cells. Then we get the chi-square, calculated chi-square. Let's do that. So that means we have to subtract this subtract expected from observed and divide it by expected. When we subtract observed from expected, then we square it and divide it by expected value. So it looks like we have to create another table here. Let's put this table down here, and we can get the values. Let me erase this so that I can get rid of the functions or formulas. Now I'm gonna get the difference first, parenthesis, this minus expected to the power 2, and then parenthesis again, and then this divided by the expected value again. All right, now we have this number. Similarly, if we drag this rectangle down below, let's see what happens. Blue minus red divided by red. Okay, looks like we're doing well. Again, blue minus red square divided by red. I can drag this over here to check blue minus red over red, and then it's pretty easy for me to drag this whole row here. Blue minus red square over red. Okay. Now I can calculate the sum of all these numbers to get the calculated chi-square. The calculated chi-square is 224. I have rounded this. If I don't round this, then it's 224.116, which is exactly equal to what we calculate here, 224.116. Now we want to check the critical region. That means we need to have a critical chi-square to check if we can reject or fail to reject the null hypothesis. So our calculated chi-square is 224.116. To get the critical chi-square, that is the threshold level, we can use Excel. So what we know so far is our alpha is 0.05. That was given in the question. That is our level of significance. And we also want to know the degrees of freedom. And what is the degrees of freedom in this case? Notice that we have 4 categories here and 3 categories here, right? So for degrees of freedom, we have, since we have used one mean for each type, so 3 minus 1 and 4 minus 1, then 3 minus 1 is 2, because we have 3 rows and 4 columns. 3 minus 1 is 2, and 4 minus 1 is 3. 3 times 2 is 6. So that means our degrees of freedom is 6. Now this is our calculated chi-square. Calculated chi-square. Now the critical chi-square, or the threshold level, is, notice that we have the probability this 0.05, we have this probability here, this region, this blue shaded region 0.05. What we want is this threshold. So we are going in an invert direction. We have the probability, we're trying to get the score or the value. So I'm gonna use chi-sq dot inv, that stands for inverse, and then rt. Rt is right because we are only using the right tail of the distribution. Right tail of the distribution. So on the right tail, we have it. The Excel asks you for probability, and we know that probability is alpha is 0.05, and the degrees of freedom is 6. Then we get the critical chi-square 12.59. So right here is 12.592. So since our calculated chi-square is bigger than critical chi-square, we reject the null hypothesis. That means our calculated chi-square is somewhere here or somewhere down the line, but the critical chi-square is here. Since the calculated chi-square is way different, way bigger than critical chi-square, we cannot say that their difference is close to 0. So that means we reject the null hypothesis. That gives us the conclusion that the data suggests there is sufficient evidence at the 5% level of significance to conclude that happiness and marital status are dependent. We conclude that happiness and marital status are associated with each other. What if we use p-value method? That means we want to get this calculated chi-square as the threshold. In other words, what is the area that is beyond this calculated chi-square? Just like the blue area here is beyond this 12.592. But let's say we have 224 somewhere here. Then what is the area right to that threshold, 224? For that, to calculate that in Excel, we can get, now we have the score, we want to get the probability. So it's not inverse, it's the correct order. So chi-square point dist, as in distribution, point rt, that is the right tail, and is asked for the x value, that means the value on the x-axis. So you put 224.116, that's our calculated chi-square, and the degrees of freedom 6. You press enter, and then you get a number that is very, very low. And that also is the p-value of our chi-square. That means this is the lowest level of significance where the null hypothesis could have been rejected. That means if we have 224 here, or of course it's only 12, so 224 will be somewhere way to right to this point. But let's say it's here. The area of this blue region beyond 224 is so small, it's very close to 0. That means the p-value is smaller than the hypothesized critical region of alpha equals 0.05. Since p-value is smaller than alpha, we again reject the null and attain at the same conclusion that happiness and marital status are dependent.